In a recent talk, we discussed the underlying common structure of paradoxes and presented our own positive theory of paradox, which we call the recipe. In today's talk, we're going to start by briefly sketching out the recipe. And then from there, we're going to talk about the possible uniform solutions the recipe suggests. After that, we're going to present our own solution, which utilize the notion of groundedness, and we restrict cut. And finally, we're going to have a little discussion on why restricting cut is more appealing than getting rid of cut completely. All right, so let's start with the recipe. So in order to construct a paradox, we need three ingredients. First, we need a partially transparent predicate with these two rules. I'll explain why I'm calling it partially transparent with an example shortly. But the two rules say if we can prove phi, then we can prove that phi is p, and phi is p entails phi. The second ingredient is a partial negative modality M, where we prove from A with empty on the right-hand side to MA with empty on the left-hand side. The crucial part is the partially transparent predicate must appear in M. In that case, we call it a partial negative modality. It's a method for finding the paradoxes. Again, this will also become clearer in the next slide with examples. Finally, if we're doing something like Gödel coding, we need a diagonal lemma to let a sentence be its partially or partial negative modality. All right, so let's take an example with the truth predicate. We usually have full transparency for the truth predicate, but that's not necessary to construct the liar and carry. All we need is a partial transparency, so filling out the same schema previously. T1 says if we can prove phi, then we can prove that phi is true, and phi is true entails phi. We can also write T2 as the following if we want to avoid cutting too much. But for now, we're going to use it this way unless specified otherwise. So why is it partially transparent rather than full transparent? We don't have the following rule when either delta or gamma are non-empty, right? Or in other words, we don't have the opposite of T2, right? But we don't need full transparency to construct the paradoxes. Let's find partial negative modalities, which the examples I'm going to give is the liar and carry. So starting with your favorite letter, let's say lambda, with T2 and cut. Again, cut is not necessary if we use the other form of T2. And right negation rule, we can get lambda is not true. Now, this is a partial negative modality because it fits the schema of that definition. So in other words, lambda is our A here, and lambda is not true is our MA, right? Similarly, for carry, we start with our favorite letter, kappa. We use T2 and cut. Again, cut is not necessary. But what is important here is weakening. That suggests that we can put anything here, regardless if it is a false sentence, a true sentence. It is still going to be a partial negative modality. And those partial negative modalities are paradoxical once we use the third step, right? So with weakening, we put absurdity here. With right arrow rule, we got if kappa is true, then absurdity follows. This is our A, this is our MA, so this is a partial negative modality. From there, we can use the diagonal lemma to let lambda be its partial negative modality. Lambda is not true, and let kappa be its partial negative modality. If kappa is true, then absurdity follows. Given these three ingredients, we can now construct the liar and the carry. This is your usual liar paradox, except a little bit longer because we don't have full transparency. But it is the same way. It uses the truth rules, negation rules, definition of lambda, and contraction and cut, right? Similarly, for Carey's paradox, it uses arrow rules, definition of kappa, truth rules, and contraction and cut, right? Sorry, this cut is not necessary, but this one is, right? Because we can use the other form of T2. Again, this is your usual Carey's paradox, a little bit longer because there's no full transparency. But what the recipe shows is that the truth predicate is not the only predicate that can be problematic, right? Because a lot of other predicates would fill out the ingredients of the recipe. For example, the provability predicate seems natural to say if we can prove phi, then it is fair to say that phi is provable. And phi is provable entails that phi is the case. So it's fair to have these kind of rules for the provability predicate. From there, we can construct probability paradoxes such as probability liar and probability carry. The probability carry is usually used in Love's theorem, and the probability liar has the same sentence as Gödel's first incompleteness theorem, but they're not the same because in Gödel's first incompleteness theorem, we do not have P2. So we cannot prove a sentence and its negation in it with the probability predicate. But once we have these two, we can have paradoxes that look exactly like these two, the liar and the carry, except probability predicate instead of truth. Similarly, for Noah's paradox, follows the same way, and what we're going to call knowability carry. And that's because is known or is knowable has the same format as the other predicates. So if we can prove phi, then we know phi is the case or phi is known. If phi is known, then it better be the case, kind of thing. Here we have a validity predicate, and it also fits the recipe or the schema that we're providing. The only difference is it is a two-place predicate, and we're basically using VP and VD of Beal and Mersey. The only difference is we push the alpha to match the style of our recipe. From there, you can get the validity carry. And the validity carry sentence is, unsurprising, a partial negative modality. Similarly, with Grelling-Nelson paradox, we use a two-place truth predicate, so true off. For example, if we have alpha is phi, then we can prove that phi is true of alpha. Similarly, phi is true of alpha entails alpha is phi. And then from there, we can get something like the heterological sentence, and whether heterological is heterological, and we can construct the Grelling-Nelson paradox. Russell's paradox in terms of extension follow the same way, exactly the same moves as the Grelling-Nelson, with the exception we use a membership schema or a two-place membership predicate. We usually have a membership schema where it's fully transparent, but we do not need full transparency. Again, we only need these two rules, which says if alpha is phi, then alpha is in the extension of phi. And then you get something along the lines of, say, the extension of phi is in the extension of phi, and the extension of phi is not in the extension of phi. So we get Russell's paradox in terms of extensions. So this sums up the talk we had earlier about the recipe for paradox. What I want to look now is for the suggested solutions from the recipe. First, we want our solution to adhere to the principle of uniform solutions, which basically say the same kind of paradoxes require same kind of solution. And all of these paradoxes that we've mentioned, Russell's paradox in terms of extension, and Grelling-Nelson, Noah's, and validity, we show that they are of the same kind, and therefore they must have the same kind of solutions. So modifying the T schema alone would not provide a uniform solution, and that is because there's nothing special about the truth predicate. There are other paradoxes of the same family that do not use the truth predicate or the T-schema. So if we wanted to really modify the T-schema, say by targeting T1, and still adhere to the principle of uniform solution, then we would have to target each rule for each predicate. So P1, K1, M1, V1, and so on. So every instance of the rule A of our ingredient, right? Similarly, we would not be providing a uniform solution if we took a hierarchical approach or singularity approach for just the truth predicate, because either approach would need also to be applied to each predicate. And these are not the only predicates, by the way, the ones I mentioned here. They're not the only predicates. There are a lot more that you can find that fit the schema. So what does the recipe suggest in terms of solution? Well, there are three possible routes. First, we can target the rule A or B from our partially transparent predicate. So target all T1, P1, V1, and so on, or T2, P2, V2, M2, and so on. Or we can target all methods of allowing sentences to be their partial negative modalities. Or we could target a structural rule such as contraction or cut. That being said, these are possible options, but they're not created equal. For example, targeting structural rules such as cut or contraction has further theoretical virtues. First, targeting a structural rule provides a single solution, for example, restrict cut, to solve all paradoxes at once rather than providing similar solutions to different paradoxes. For example, placing similar restrictions on each of T1, P1, V1, and so on. Moreover, targeting structural rule require a single justification, whereas a stratifying solution, for example, must justify the stratification of each partially transparent predicate. Similarly, rejecting the rule A would require a justification for rejecting each instance of it. So you must have a justification for rejecting T1. Why shouldn't the truth predicate have that rule? Why shouldn't the probability predicate have that rule? So P1, and so on. All right. Speaking of the solutions and the structurals, targeting structural rules, that's what we're gonna do. We're gonna target the rule cut by restricting it with the notion of groundedness in hand. So let's talk about groundedness informally first, and then we're gonna provide our formal account of groundedness and ungroundedness. So informally, it doesn't differ from other people, right? It doesn't differ from Kripke, Leitgeb, Diablos, and Simmons. So for example, this is a small example of grounded sentences. A1 says A2 is false. A2 says A3 is true. And A3 says snow is white. To determine the truth value of A1, we have to determine the truth value of A2. To determine the truth value of A2, we have to determine the truth value of A3. And we know snow is white is true. So this A3 gets its truth value ascertained. From there, A2 is true and gets its truth value ascertained. And then from there, A1 is false because it's saying A2 is false when it's true. So it also gets its truth value ascertained. So in this instance, this is a grounded example. An example of ungrounded, say if A2 said A1 is true, then we get stuck in a loop kind of thing, and we can never determine their truth values, or their truth values never get ascertained. Even though I'm talking about truth values here, our formal notion is purely syntactic, and it is a little bit different from Simmons' approach, but it uses trees as well. Simmons' approach, he would use basic trees and then pruned trees. For us, we only have what is similar to his basic tree. We're gonna call groundedness tree. Basically, we open up the sentences and look inside them, right? So have not P of negation. If we have conjunction, disjunction, conditional, we branch to each sentence of them. And finally, this is the important part, is if we have a predicate that is partially transparent, for example, alpha is P, we look at what alpha is. So we look at the referent, right? Again, this is only for the partially transparent predicates. If the predicates are not partially transparent, then we don't go on, the branch would hold, right? So let's take our previous example. So let's see how A1 is grounded. So again, A1 says A2 is not true or A2 is false. We're equating false and not true. We start by getting rid of the negation. We look at A2 is true, and then true is a partially transparent predicate. So we look at its referent, namely A2. A2 says A3 is true. Again, true is partially transparent. So we look at its referent, A3, and A3 says no is white. The predicate white is not partially transparent. There's no more moves. The tree holds. Therefore, the sentence A1 is grounded. In fact, each one of them is grounded, right? As an example of an ungrounded sentence, let's look at the liar. We start with lambda is not true. We get rid of the negation. Lambda is true. True is a partially transparent predicate. So we look at its referent, which is lambda is not true. And we get stuck. We have an infinite regress of a branch, right? The branch never holds, therefore the liar sentence is ungrounded. Similarly with carry, we branch off our conditional. In absurdity, there's no more moves. In this section, we have kappa is true, this is partially transparent, and we open to kappa again. And we get to do the same thing over and over again. And since there's at least one branch, and that's important, at least one branch that doesn't hold, we say it is ungrounded. It is important because we take our ungroundedness to be contagious. So if you want to think of it semantically, it's weak-Kleene-esque. So in any instance where we have an ungrounded sentence disjuncted or conjuncted with any other sentence, the whole sentence is going to be ungrounded, regardless whether that sentence is true or false, right? We're not going to talk a lot about quantifiers, but just for completion, existential quantifier and universal quantifier. So for example, if you have, there is an x, phi x, and for all x, phi x, then the tree splits of every instance of phi a in the domain where a is a name of the instance. So for example, in Yablo's paradox, we have each sentence say every sentence below me is not true. So for example, S1 is saying S2 is not true, S3 is not true, S4 is not true, and so on. So when we branch the sentence S1, we're going to branch to every instance of its domain. So it's going to say S2 it's not true, and so on. And we're going to see that none of the branches hold, so it's ungrounded, but we only care about one branch not holding to call it ungrounded. Right, so how about our logical system now? Our logical system is purely classical. Choose your favorite standard rules of classical logic, whether it's additive or multiplicative, doesn't matter. So our operational rules are all the same as classical logic. Similar with our quantifiers with the usual restrictions on universal right and existential left. As for structural rules, we have everything that classical logic has, including cut, but with a little restriction here. And the restriction is the cut formula A cannot be ungrounded. So we can use cut all the time as long as A is not an ungrounded sentence. And that's the only difference from our logic and classical logic. So to look at an illustration of where the restriction happens, and for example, the liar and carry, it always happens at the last step because we're cutting an ungrounded sentence. Lambda here is ungrounded, and we're using cut to get to the empty sequence, and that's not possible in our system. Similarly with the query, we're cutting a query sentence which is ungrounded and thus reaching absurdity or proving anything that we want out of thin air is not possible. All right, so why should we restrict cut instead of get rid of cut completely? So we take our project to be a solution to semantic paradoxes with minimal deviation from classical logic. After all, classical logic is not the enemy, the paradoxes are. So in other words, we subscribe to the maxim of minimal mutilation. That's from Hortland, which he says, when revising a theory, we ought to disturb the theory as little as possible. So in a nutshell, the maxim requires that a non-classical theory does minimal damage to classical logic while simultaneously accommodating a transparent truth predicate. And that's what we're doing, right? We can accommodate full transparency. We don't have any problem with it because the paradoxes are not going to arise because we block them at the last step. That being said, cut-free, fully non-transitive logic still mutilate from classical logic more than they should. So as an example from Hortland and Ripley, the non-transitive have to be very careful when it comes to accepting non-standard operation rules. So sequence-style natural deduction rules, such as a form of modus ponens, for example, and that applies to us too. We have to be careful, but I'm going to show you a little difference between us, right? So for example, this instance of modus ponens can simulate cut, and as a result, we can use that simulation of cut to construct Carey's paradox because it's an instance of cut that is used for Carey's paradox. Other sequence-style natural deduction elimination rules also have versions of cut hiding in their bushes. For example, argument by cases and principle of explosion can also simulate instances of cut. And as a result, the fully non-transitive must reject all of these rules, right? So to avoid the paradoxes and simulating cut to get to the paradoxes, the fully non-transitive theorists must reject these rules since cut likes to hide in their bushes. On the other hand, our approach does not need to get rid of every bush cut likes to hide in. We can keep all of the inference rules of classical logic in sequence-style natural deduction with the little caveat with the same restriction that we have on cut. So elimination rules must still be restricted in the sense that the eliminated formula cannot be ungrounded. So we can still admit modus ponens. So modus ponens is allowed in our system as long as A, here where we affirm the antecedent, A cannot be ungrounded. Similarly for argument by cases and principal explosion and other elimination rules. All right, another way to highlight the difference between our approach and fully non-transitive is to make use of the notion of classical recapture. So classical recapture is used as a method by the non-classical logician to show that their logic can retain classical reasoning in most scenarios. At least you can reason classically as long as you're not in a problematic domain. That's the whole idea. And the main motivation for relying on classical recapture is that the non-classical logician typically rely on classical reasoning in the meta language. And that is because usually their logic is too weak to prove important mathematical and metalogical results. That being said, classical recapture comes with its own set of problems and that need to be addressed. I'm going to mention 3 problems that I'm not going to go in details with or for. And then afterwards, I'm going to mention a 4th problem and I'm going to focus on the 4th problem. So these problems are mentioned in Rosenblatt, where they credit Williamson. The first problem is that the non-classical logician usually claims that it is safe to reason classically in non-problematic domains, but they fail to establish what it means for a domain to be non-problematic. Second, appealing to classical recapture can be regarded as an ad hoc approach, and that's because classical recapture was only considered when the non-classical logician faced a a problem in proving crucial mathematical or methodological results. And third, it can be very difficult in terms of specifying when classical logic can be retained and when it cannot. But the main problem I want to focus on is that a problem raised by Woods, which pertains to proving recapture result. The non-classical logician must be careful in proving recapture results so that they don't prove recapture results using principles that they reject themselves. So for example, a non-transitive theorist want to prove recapture result, they must prove recapture results without using cut, for example, or its equivalent, right? So Wood's claim, if we have to decide between two logics, let's say classical logic and fully non-transitive logic, a cut-free logic, then we have to adhere to what he calls the principle of logical partisanhood. He says, unless the output of weighing the merits of my background logic against an alternative, on one hand in the light of my own background logic, and on the other hand by the light of the proposed alternative, agree that moving to the alternative is no worse than staying with our current background logic, we ought to hold fast to our background logic. So for example, using classical logic as background logic, then giving classical recapture, both classical logic and the cut-free non-transitive logic are about the same strength, because the classical recapture shows that we can do everything that we want to do classically in non-problematic domains. But presumably, the cut-free logic does better in terms of informativeness. On the other hand, using the cut-free logic as the background, so here, because the cut-free has an advantage, we move to the new theory, the new logic, right? We move to cut-free logic. Now we look at the other hand using cut-free as a background logic, but since we do not have recapture results, since the results of recapture are done with the lens of classical logic, then classical logic is presumably better in terms of strength in comparison to the cut-free logic. And so we have to switch back to classical logic. So once we have adopted the cut-free logic, the score changes. And the new score suggests switching back to classical logic, and away we go. Another way to put it is by Priest. A worst case scenario is one where we simply flip back and forth between two logics, each of which is better according to the other. So a fully non-transitive must prove classical recapture results without using transitivity, without using modus ponens, without using argument by cases, explosion, and so on, in order to claim that we should adopt their cut-free logic over classical logic. On the other hand, for us, we do not need classical recapture results for our system. And I'll explain why we don't need classical recapture in the next slide. But even if we did, the use of transitivity in the background logic should be permissible in both classical logic and our system, and hence satisfying the logical partisanhood. So in other words, a proponent of a cut-free approach would have to carry these problems if they want to retain as much of classical logic as possible. On the other hand, cut is available to us in our approach as long as the cut formula is grounded. So that is, we have full classical logic except in problematic circumstances. And we specify what are the problematic circumstances, right? It's when the cut formula is ungrounded. Therefore, we do not need classical recapture for our system, since our system already achieved the intended use of classical recapture without taking its baggage of problems, right? So in a sense, classical recapture is already built in our system, because that's the whole idea of restricting cut. Thank you.